let's get started. This is the final piece of puzzle to complete the discussion on database kernel. Okay, so we talk about transactions, and we talk about transaction needs to satisfy these properties, where this stands for and we know that isolation, now we understand how we actually realize isolation, which is through concurrency control. Sometimes people claim isolation is realized by using locking. That's simply because one way of doing concurrency control is by locking. But not necessarily we will always use locking for concurrency control. I briefly mentioned a few other concurrency control schemes like OCC and VCC. None of them actually use lock. Okay, but the one of the popular choices is by locking, where we talk about in particular talk about these two, where they only allow serializable schedules. They only allow serializable schedules. Okay. And consistency, we explain this. This is basically just to ensure all functional dependencies are met. That's essentially what it means. And atomicity means that all or nothing. All or nothing. So we haven't so far. These two, A and D, is what we haven't talked about yet. How exactly we're going to realize atomicity and durability? That's essentially what we're going to talk about today, which is crash recovery, which covers, obviously the title suggests that we're going to talk about durability. But in a way, it also takes care of atomicity, which you will see in a minute. Okay? Note that atomicity goes both ways, means that it's all or nothing, meaning that if a transaction has committed, you need to ensure all actions are permanently reflected on database at some point. Or when transaction aborts, either because the transaction itself wants to abort or is forced to abort by system crash, none of its actions should be reflected in the database. Okay? That's what atomicity means. So this is a quick review of atomicity. Now let's look at a simple example, which is given in this graph right here. I have 5 transactions. 1, 2, 3, 4, 5. And suppose the green line, this is the time dimension by the way, the x-axis is the time dimension. And the green line indicates the timestamp when system has crashed. So my system has crashed at this point. The question is, in order to satisfy the ASCII property, what should DBMS do in this particular case? Well, you should roll back the changes you have made for T4 and T5. You should roll back them, because all or nothing. Okay? Roll back them all the way to the beginning of these transactions respectively. What about T2? Do you have to do anything about this? Some of you says no, some What about T2? Do we need to do anything about it? The tricky observation is, the tricky thing here is, even though T2 has aborted before system has crashed, there is no, however, guarantee that it has finished the abort process. Maybe by the time the system has crashed, T2 is still in the process of aborting, in other words, rolling back its actions. Do you guys follow me? So after system recover from this crash, you, database management system, need to verify and ensure that I have actually completed the rollback process will keep you. And you need to verify, and if it's not the case, you need to continue the rollback process, pick up from where it's left. What about T1 and T3? Do you need to do anything about it? Well, you need to ensure durability, meaning that the changes made by T1 and T3 are permanently reflected in your database. This is not so obvious from the beginning, because you may argue, is it the case that when T1 and T3 commit, the changes made by those transactions are permanently reflected on disk already? The answer is no. That's not the case, because we have the buffer manager. Okay, and with the buffer manager. T1, T3 commit only means that they tell the database management system that I have committed, and it's now your responsibility to make sure my changes are permanently reflected on disk at some point in your database. Okay? I have finished making the updates to the pages that are maybe in the buffer. When does those 30 pages get pushed to the disk? That's not my business. That's the job of the buffer manager. I don't care when you do it, but once I commit, you need to ensure that these 30 pages get to push to disk sooner or later. This brings up challenges because when system has crashed, the buffer is gone. The buffer is gone together with all the 30 pages in the buffer. They are gone. They're lost forever. However, if it is a dirty page caused by an update from a transaction that has committed, you cannot let go. You have to somehow recover that dirty page and make it permanent to disk at some point. That's the point of commit. Okay. So in high level, T1, T3 should be durable, T2, T4, T5 should be aborted. Okay? So in this lecture, we're gonna spend the entire lecture discussing exactly this point, how exactly this is done. Okay? And it's not a trivial subject. So I do ask for your attention. Okay? So we'll assume we are using straight 2PL. What does it mean? That means we are only dealing with serializable schedules. We're only dealing with serializable schedules. And there is no cascading abort. And updates are happening in place, meaning that we're not using a multi-verted database. We are not using a multi-verted database. Okay? Later, if I got time, I will show you what a multi-verted database looks like. I have a slide for that. Okay? Number one is, can you guys think of a simple scheme, very simple scheme, that give you atomicity and durability somehow, magic.
Is it a log?
Huh?
Is a log?
Log is, yes, but log is not necessarily a simple scheme, right? So what about if you don't use log?
Never return OK until you've written this.
Never return OK somewhere back, meaning that you do not allow a commit on all the data pages caused by this transaction has made to disk. And that obviously ensures what? That ensures durability, because once a transaction has committed, you know if you're using that particular scheme, you know for sure all the changes made by that transaction is updates to override committed data on disk. What does this guarantee you? This ensures atomicity, right? Why? Why this help ensure atomicity, Jonathan?
No steal.
Yeah, let him see.
The no steal of force policy.
No steal policy. Why this helps ensure autonomous payment?
Because you have to, when you want to commit, that means the entire thing has to go from the buffer manager to disk.
That's durability, right? What about autonomous? Why no steal policy helps autonomous?
No steal policy.
No steal policy, yes. The first one, yeah.
You have unlimited updates and you let them into buffer manager, that violates the nothing part of the
Yes. What's your name?
Anitash.
What he said is, if you do allow this to happen, on the contrary, right? You do exactly the opposite. You allow uncommitted updates to override committed data on disk. What happens? Well, if this transaction later aborts, you need to worry about cleaning up the corresponding disk page, because now you have a disk page that holds uncommitted data. Whereas if you use no steal policy, think about what happened. If the transaction aborts, do you have to worry about anything? Well, all you need to worry is to mark this page as not dirty. Then you're done. Because the change made by this uncommitted transaction, you know that if you're using no steal policy, none of the changes made by an uncommitted transaction has made its way back to disk. Right?
But it wouldn't guarantee, you wouldn't have like isolation, right? Because other transactions could be using that same buffer.
Well, isolation is our orthogonal issue. We assume we are using straight two-phase locking in place. So that's an orthogonal problem, actually. Has nothing to do with it. Because, do you
Yeah,
think
that
that
makes
one?
sense, yeah.
Okay. Okay. So we got this combination. So essentially we got a combination that says force and no steal.
Would you also need to, if the transaction aborts, read the old version back from this?
If you are using no steal, that's exactly what you don't have to do. Because it's no steal. If the transaction aborts, you know that none of the changes made by that transaction has made to disk. So you don't have to worry about reading the old data back. You just throw away the corresponding data pages.
But if it releases the lock on the data and another transaction tries to read.
Well, by the time you release the log, the one thing you need to do is to throw away the dirty page made dirty by that transaction from the buffer. So if somebody else tries to read that same data item, now they have to read data from this domain, which holds the old data to begin with. Make sense? You just throw away dirty pages by this transaction.
You just have the page to the free list or whatever.
You just flush away this page from the
Well,
buffer.
what if you've got two transactions, the first one starts, changes the data in the buffer, releases, it hasn't committed yet, a new one picks up.
So it has a significant, it has a performance implication, which is when regardless how many pages, how many transactions are being in this page, if it's affected by a aborted transaction, you just throw away this. The other transaction used to be a buffer hit for them, now they just need to grab the data again from the system.
And the second transaction.
Because one thing to keep in mind is isolation is taken care of by the concurrency control module. So there's no conflict to begin with. Does that make sense to you? So this policy, if you combine them, this gives us atomicity and durability for free, quote unquote, for free. However, it's really expensive, right? If you think about it. Why? Because you interfere with what the buffer manager is supposed to do. Another person comes in and tells the buffer manager, oh, no, you cannot do this. No, you cannot do that. There are two scenarios this happens. One is no steal. When buffer manager tries to push a dirty page to disk, no steal policy may come and say, oh, you cannot push this dirty page yet. It's not committed yet. Okay? And fourth, the other thing says, the transaction cannot commit until buffer manager push all the dirty pages to disk, and this may happen who knows when. So the transaction may be ready to commit at time 10, may have to wait until time 100 or time 1000, and still not be able to commit. Simply because buffer manager hasn't got a way to turn around and push all the dirty pages by this transaction to disk yet. Okay? So this combination gives you atomicity and durability. However, it's a really bad combination from the efficiency point of view. It's a really bad policy from the efficiency point of view. So what would be a good policy? A good policy would be, first of all, you do not block transaction to commit. Transaction commits whenever he or he wants to. Whenever the transaction wants to commit, you let that transaction go ahead. Okay? And you do not interfere with what buffer manager is supposed to do. When buffer manager tries to write a dirty page to disk, you let it do its job. You do not come in and tell the buffer manager, you cannot do that because it's a dirty page by an uncommitted transaction. So that gives you exactly the opposite, which is no force and still. Right? No force means that you do not block transaction to commit. Transaction can commit whenever he or she wants. Still means buffer manager can push dirty page to disk just as it's used to be doing, using whatever buffer replacement policy to the discretionary of the buffer manager. Okay, that's precisely the next slide. Okay. So this gives you this graph right here. So we have all these combinations. No force and still. This clearly will give you the fastest performance because that's the most efficient one, as I talked about. Because it doesn't block transaction to commit and it doesn't interfere with what buffer manager does. So obviously this gives you the best performance, efficiency-wise. And this obviously gives you the slowest performance because it blocks transaction to commit and it blocks buffer manager from writing dirty pages. So it introduces significant performance overhead, so this must be the slowest. You can of course also do this corner or that corner on top, meaning that either you do not block transaction to commit or you do not block buffer manager to write dirty pages. But you do not do both at the same time. Okay? So efficiency-wise, that's the best. This is the worst. Isn't that, by looking at only the figure to the left, you may argue, okay, isn't the choice clear? Just no-brainer, we should go with this. However, that's assuming system never crashes. If you have a system that indeed never crashes, yes, you go with that. But in reality, the system does crash, right? For whatever reason, disk failure, bug in your system, or power failure, or in a distributed system, network failure, whatever, right? There are many, many reasons the system can go bad in reality, right? So if you look at the same picture, now consider the potential of system failure. It's a different picture now. It's totally a different picture. If you use this, as we argued earlier, both automatically, which means you don't have to worry about redo. Redo is to ensure what? It's to ensure durability. When system has crashed, for transaction that has committed, you might need to redo its action to just make sure the changes are reflected in the database. For example, a transaction has committed, but the change made by that transaction is only hosted by the buffer manager at the time the system crashed. So when system has crashed, that change is gone forever. But because the transaction has committed, when the system back online again, you need to redo that action so that it's reflecting the buffer once more, and at some point later, buffer will kick that dirty page back to disk. Now it's permanent. So you need to worry about redo for durability. Do you follow me? That's what we call redo. And some of you may immediately realize there is something going on here, right? The naive solution is whenever a system has crashed, I look at what transaction has committed, and for all the transactions who have committed, I redo all their actions, just to be safe. That obviously is a naive baseline. It works because it guarantees you that you will be able to restore all the actions by those committed transactions. But efficiency-wise, it's really bad. Because you may have, I don't know, 10,000 transactions who have committed by the time system crash. Are you telling me to redo all of them? When in fact, many of them may have already been pushed to disk by the buffer manager before the system crashed. So the whole point of this game is to figure out the right amount of work that you need to redo. And don't over-redo. But you have to be careful. You cannot under-redo, because if you under-redo, you violate the requirement of durability. So that's a delicate balance you need to play. Okay, so that's redo. What about undo? Well, undo is with respect to atomicity. If a transaction has not committed yet and system has crashed, what happens? Well, some of its changes might have been pushed to disk. Some of it may not be pushed to disk. If you are using what? If you are using steal policy. If you are using steal policy. If you are using steal policy, that may happen. And what happens when the system is back online? Well, you need to undo those actions that have been reflected on disk. You don't have to undo those that had been executed before system crash, but the changes had not been pushed to disk yet. Of course, again, you have a naive solution, which is undo everything. But if you propose that to Amazon.com, if you think about how many active transactions Amazon.com has at any given time, and you tell Amazon.com, if your server crashes, I can guarantee you ASCII property. Undo all the active transactions at the time system crash. And we're talking about millions of transactions. You are performing a lot of unnecessary efforts, because many of those may not have been reflected on this anyway. You don't have to undo them. But in the worst case, you may need to undo all of that, right? So if you use steal and no force, you need to worry about both undo and redo. But if you use no steal and force, you don't have to worry about either of them, because it's taken care of automatically. Do you guys follow me? So now with both pictures in mind, which is better is not clear, right? Which is better is not clear. Because during normal execution of the system, still no force is the best, performance-wise. But once you have system crash, force, no steal become the best, because you don't have to do anything when system has crashed. Right? So overall, which is better? If we were to bluntly implement redo and undo as I argued in the naive solution, which is redo everything that has committed and undo everything that's still running, then the choice indeed is not clear. It depends on how often you system crash and how many active transactions you have and how many transactions has committed at the time of system crash. Do you follow me? However, we're going to use a particular mechanism, which is suggested by Charlie, using log to facilitate us to do undo and redo in a way that almost always undo and redo, in this case, even though you are using steal and no force, it's not going to be too expensive. In other words, you can somehow recover the state of the buffer manager right before the time system has crashed. Because that's all you need. If you understand the state of the buffer manager right before system has crashed, you know what 30 pages have been written to the disk. That gives you enough information to minimize the amount of work to redo and minimize the amount of work to undo. Do you follow me? Because that precisely tells you what uncommitted updates have been pushed to disk and what committed action have been pushed to disk. In other words, how many committed updates have not been pushed to disk and how many uncommitted updates have not been pushed to disk. And those are all you need to know to minimize the amount of work you need to do redo and undo. Do you follow me? Okay, so that's essentially what we're going to talk about next. Okay? That's essentially the entire remaining part of the lecture. One thing though that complicate this whole game. If you have only one system crash, this game is not that bad. I mean, I can probably finish the discussion in 10 minutes. However, during the redo and undo, when you try to recover from a system crash, what may happen? It may crash once more. And when you come back from that, when you recover from that, when you try to redo and undo for that crash, which is crash after crash, it may crash once more. This reminds me of this movie, right? Have you watched this movie called Inception? Which is you have levels of dreams, and one critical thing for you is to be, I mean, no kidding, I mean, that's precisely what we are heading into, essentially, is to figure out which level of dream you are in. And somehow that matters. And same thing here, you need to, because think about it, do you undo is an update operation by itself. Undo is an update operation, right? You need to worry about redo the undos, because an undo is an update operation supposed to be permanent, but a crash after crash may eliminate the undo effect. So you need to worry about redo the undo. But you never need to worry about undo the undo, because undo the undo means that you have done nothing. So undo is a concept to the system, but from the database point of view, it's just another update operation. How do I know I should redo this update or undo this update? It really depends on whether it's an undo update or redo update to begin with. You follow me? So you redo the undo, but you never undo the undo. Right? And you redo the redo, but you never undo the redo. So it's kind of like figuring out which level you are in and then carry out accordingly. You follow me? And you can already see how this gets complicated, right? Fortunately, we have a way of doing all this. So in the movie of Inception, I forgot how they figure out. There's a way for them to figure out whether you are in a dream or not. So similarly, we have a mechanism for you to somehow keep track of things. Okay? So that's what I'm going to talk about next. And this is the famous Iris algorithm. So Iris algorithm was first formally proposed by this guy from IBM Research called Mohan. But before him, there were tons of work in the literature that kind of make this kind of like folklore kind of thing. And he, for the first time, formalized this notion. That was in, I think, sometime in the 80s. Sometime in the 80s. Okay? And that's what we're going to talk about next. The basic idea is logging. So you record the redo and undo information in a place called log. And this log is nothing else but a file. And why we call this log is from this, for any tree you have a log that tells you how this tree grows over a year. And that's how people get the inspiration from. That's why they call this particular file log, right? Which is to capture just the essential information needed for carrying out redo and undo. Carry out redo and undo. And there are a couple of notes you need to remember. We only do sequential writes to the log file. We never do random updates to a log file, meaning that you only do a append operation to a log file with new and incoming log records. So it just keep coming with new log records. And each log record has a particular format. And typically a log record has a format like this: transaction ID, page ID, offset, length, old data, new data. This immediately tells you one thing, which is you only create a log record for update operations. You never need to create a log record for read-only operations. Why? Because for read-only operations, you don't have to worry about redo, you don't have to worry about undo. Only the update operation that you need to worry about. And that's why this log record tells you it is this transaction trying to update this page at this offset location. Offset refers to the offset we talked about in the heap file implementation, which is from project 1, right? For this much length, so I'm updating from here to here, this many bytes. And that's the old value for those bytes. And this is the new value for those bytes. I'm overwriting this. And once with this information, you can either do redo or undo, right? You can do both. You can do redo, you can do undo. Undo is very easy. You take this value and overwrite that. Redo, you take this value and re-overwrite that. You follow me? So that's a typical log record. And then in addition, log file, in addition to this log record, has additional control information, which I will introduce in the next few slides. But only having these log records like this, is not enough. Because log is a file, and you write log record to log file. And these writes may fail as well. There's no one guarantee you that all the log records are permanently on disk by the time the system has crashed. Right? So merely having log and having log record like this is not good enough. We need something more. So that's what we're going to talk about next. And a particular idea people have proposed, and this has been pretty much used not only in database systems, but in almost literally all systems that need to worry about crash recovery and durability. They use some idea similar to this, which is called red hat logging, WHL. Okay, what is red hat logging? Well, red hat logging has only two rules, which is actually quite simple. Rule number one, must force the log record for an update before the corresponding data page gets to disk. Second, must force all log record for a transaction before commit. The second is actually easier to understand. Let's go with that first. Recall that we talked about the force policy at the beginning. What is the force policy, by the way? Force policy says a transaction can only commit when all dirty pages caused by that transaction are pushed to disk before it commits. But that's a fairly expensive operation. Here, we modify that a little bit. You do not force all the dirty pages caused by this transaction to disk. Rather, you force all log records for this transaction to be written to disk. Then allow this transaction to commit. It's a subtle difference, but that makes a huge difference because I may have caused, being a transaction, may have caused 100 pages to be dirty, which produce, let's say, 100 log records because I have 100 update operations, one for each dirty page. Simple scenario, right? So 100 dirty pages, which gave me 100 log records. The point is, this 100 log record may fit in just a single page, or maybe a few pages. So you are talking about writing 100 dirty pages, and those are random writes, versus writing a single page of data or a few pages of log record, and they are sequential write. Do you guys follow me? So doing this force policy, the modified version of the force policy, is going to be much more efficient than doing the original force policy on the dirty page.
Even if the log's on the same disk?
Even?
If the log's on the same disk?
Well, that's a good question. So sometimes, and in most database systems, they store the log file in a separate disk for two reasons. One is for performance, because you want to make sure you only do sequential write to that disk. If you come back and serve some random write, then do that sequential, interleaving these two, the sequential write becomes random write, right? We talked about this earlier. Second, for durability purpose, what happens if your disk fails? You want to make sure your log is in a separate disk from your database. So either you have your database or you have your log. You don't lose both of them at the same time. So we understand the force policy, right? Do you guys understand me on that? So by using this modified version of the force policy, we guarantee what? We guarantee we can do durability. We can ensure durability. Even if all the dirty pages caused by this transaction are still in buffer and they are lost later on due to system crash, I can still guarantee durability. Why? Because I can load the log records for this transaction back in from the log file and redo all these actions. The reason you can do that is because I know you can only commit if all your log records are in disk. So when system crash later on, if you have committed before system has crashed, I know all your log records are on disk guaranteed because of this. The dirty pages caused by you may not be on disk. Maybe they're on disk, maybe they're not. I don't care. But I know all your log records are. This alone will give me enough information to guarantee durability. You follow me? So that's point number one. Let's go back to point number one. Point number one, obviously concerned about atomicity, right? Number two is about durability. So number one, no doubt, should be on atomicity. But why is it related to atomicity? Let's look at it. Must force the log record for update before the corresponding data page gets to disk. Can someone explain to me why we need this? Why? Why we must guarantee this? Victor?
Because, well, disk writes are slow, so if it crashes somewhere while it's trying to get to disk, then we haven't guaranteed that it's on disk. But if we force the log before the data page gets there, so even if it crashes in somewhere in between, we've made sure that we can get that back onto disk.
Well, you are still talking about redo, right? So redo is taking care about number two. Number one is really about undo. It's really about undo. Okay, if you cannot understand why number one is needed, let's flip the order. Let's say we allow an update to a particular page to be written to disk before the corresponding log record has been written to disk. What may happen? Well, what may happen is as follows. At time t1, suppose this is time. Page p1 become 30. Okay? And that, so transaction 1 writes this, that calls this, and this produces a log record. Log record, let's say x, has a bunch of information, which I have described. Okay? And then at some point t2, the buffer manager push p1, so I'm going to duplicate the buffer here, which is still dirty. I'm going to push this to disk. Is that okay? Yes or no? Do you follow me? So the corresponding page on this, the p1 image of the image of this page on this now become the same as this, which is dirty, which was dirty, now is no longer dirty. Do all of you follow me? Now what may happen? Well, T3 crash. System crash. And note that T1 has not committed yet. What do you need to do? Well, due to atomicity requirement, you need to what? Undo. You need to undo this change. Let's say at this point, the image of P1 on this is, instead of like that, the image on P1 looks like that. You know what? Too bad. You lose that forever. Why? Because this log record, by the time the system has crashed, may not be on disk yet. So when system crash, then this is gone forever. All you're left with is this. This is gone. This is gone. This is gone. That's all you're left with. How do you undo? Tell me how you undo. If you can undo this, if you undo this, you're a genius, right?
You use magic.
Well, this is a computer science, right? It's not a business.
Magic computer science.
Okay, so no way you can undo. However, if we use this policy, what happens? Well, if you use this policy, crash still happens here. When buffer tries to do this, it will be blocked. So that P1 will be still like this. And you can only do this when, or in other words, if this becomes this, I know one thing for sure, which is this Lx. if you allow this to happen, this must be on disk already. So when system has crashed, yes, I end up with this page, which is like that. But my LX is here. I can load this back in to change this back to this, to undo that. And this is the way we allow steal. Think about one is essentially steal. You allow steal to happen because you said nothing about whether this update is by an uncommitted transaction or not. That's essentially steal. You allow steal to happen. And now you allow steal to happen only if the corresponding log record has been pushed to disk already. Okay? So that's 1 and 2. Okay? Keep in mind 1 and 2. Okay? You must remember 1 and 2. You must remember 1 and 2. You must remember 1 and 2. Important things 3 times. Okay? Now, each log record has a unique identifier called log sequence number, Allison. Allison always increase. This is easy to understand because you always do append operation, sequential write. So this number keep increasing. Okay? And each data page contains a page Allison. So in your implementation of project 1, which is heap file page, we add one more data variable to the page, which is what we call page Allison. And page Allison records the log sequence number of the most recent log record for an update to that page. So whichever log record made the latest change to that page will be kept as the page Allison for that page. Do you follow me? Yes or no? So one thing you need to remember is the page Allison for the same page, for the page in buffer and for the page on disk might be different, even though they are actually the same page. Why is that? Because what happened to the image of this on buffer, which has not been pushed back to disk yet. That will cause the page Allison of the same page, one on disk, one on buffer, be different. So the page Allison for the same page might be different for the image of the page on buffer and on disk. You follow me? Of course, they may be the same because the buffer manager may have pushed that dirty page to disk, and when that has happened, the page Allison of these 2 pages, which is essentially the same page, now are consistent.
Why did you need the page LSN to be the first log record of the transaction instead of the most recent log record? Because you have a lot of logs per transaction, right? So
well, we will explain why we need this. You're asking a why question, right? Let me present the design first, then we talk about why this is needed. Okay. And system means the DBMS keeps a global value called flush Allison. It's a single value. And what it says is the max log sequence number of all log records that have been pushed to disk so far, has been flushed so far. So think about this. This is my log sequence number. Keep increasing. Each number corresponds to a single log record. You follow me? So my latest log record might have already gone up to this value here. However, not all of them have been pushed to disk yet, right? Some of them have been, some of them have not. Max, the flash Allison, is the last record, log record that have been pushed to disk. Keep in mind, we always push log record to disk in sequential order, meaning that in increasing order. So the last record you push to disk will be the max Allison that have been flushed to disk so far. So you just need to remember the last record pushed to disk. That's your flush Allison. And this part, the dark green region, is what we call the log tail in RAM. Those are log records that are still volatile, meaning that if system has crashed, if system going to crash, you will lose this guy forever. But this guy is safe because you already get a copy of them on disk. So far, so good? Now back to Victor's question. Why do we need page Allison? Well, the Red Hat logging, how we translate rule number 1 using this notation now. We are computer scientists, right? We don't write an English statement in our code, right? We don't write this into the code. Of course, if one day you can come up with a programming language that can understand human logic, just tell the system, I want to do this and this, magically they can come up with a code that implements this logic, yeah, then it's fine. But we don't have that yet. Right? Something like that, Prolog and all that. But even in that case, you need to understand data log and encode your logic properly, not like this. So how do we enforce this logic using this notation now? Yeah.
So you just, the buffer manager will check the Allison on the page and see if it's less than or equal to.
That's exactly right. Yeah, that's exactly right. So you check this. Page Allison must less equal than flush Allison in order for the buffer manager to push this dirty page to disk. If page Allison is greater than flush Allison, even though it's a dirty page, and even if buffer manager says I need to replace this dirty page, no, you cannot do it. You have to wait until its page Allison is less than or equal to flush Allison to ensure rule number 1. That's essentially rule number 1. Okay. What about rule number 2? Oh, that's easy, right? The last log sequence number of the transaction must be less than or equal to flush Allison in order for the transaction to commit. That's it. Okay. Good. So that's so far so good. Now let's look at log record in a little bit more details. So in addition to those fields I have introduced earlier, there are additional few fields in a log record. One thing that we need to have is the previous log sequence number. And this, however, does not encode the log record right before it, but that's pointless. Why you need to do that? What it tells you is the preceding log sequence number of the same transaction. Because log file keeps log record from all different transactions. So the current log record may be from transaction 1, but the preceding log record might be from a different transaction. For reason we will see later on, which is essentially for undo purpose. You want to be able to track what is the next action I need to undo for the current transaction. For that purpose, you need to know the previous log sequence number. So I keep track of that in my log record to form a chain of some sort for one transaction, for one given transaction. Type is critical because the format I have introduced so far is for mostly for the update log record. For update log record, they follow the format I have introduced so far. But there are other types of log record. One is commit, one is abort. Obviously, you need to remember when a transaction has committed, when a transaction has aborted. That's why we need a log record for that purpose. And we need checkpoint, which I will explain later on what that means. We also need CLR, composition log record. And this is particularly designed for undo actions. Why? Because you don't want to undo or undo, as I argued earlier. So this CLR is kind of like the mechanism in Inception to figure out which level of print you are at. So CLR is to tell you this is an update operation, but it is an update operation caused by an earlier undo operation. So I was in a recovery process. So I produced this CLR record to indicate that. So if you crash again, when you try to do recovery yet one more time, you don't just undo all the update operation I'm saying. You don't, in particular, you don't undo a CLR. You will need to redo a CLR because the previous undo might have failed. So you need to redo CLR, but you never undo CLR. Does it make sense to you? What about AND? Well, commit and abort itself takes time. Commit and abort is not an atomic operation. It takes time. For example, checking all log record for the current transaction has been flushed to disk. That takes time. So from time to commit to end, there is some gap. So a transaction has only finished the committing or aborting process when you see the end log record for that transaction. And these fields are for update type record only. Otherwise, you only have those 4 fields. Okay? So that's your log record. And there are 2 more. This is just a complicated subject, so you have to remember all these guys, all these players. There are 2 more guys we need to keep track of, which is TT and DPT. Okay? And after that, I'm ready to present to you this final algorithm of the class of this semester, which is the areas recovery algorithm. But before that, we need to understand these 2 tables, TT and DPT. What's TT and DPT? Okay. First of all, let's look at TT. TT means transaction table. This actually is easy. It has 1 entry per currently active transaction. How do you define active transaction? When a transaction has not reached the end log record, it is considered active. It contains XID, status, and pass, Allison. Okay? Only 3 fields. And 1 entry per active transaction. Transaction ID, that's trivial, right? It's a unique identifier for the transaction. Status is either running, if it's before end, before commit or abort, it's considered as running. If it's between commit and end, it's called committing. If it's between abort and end, it's called aborting. So there are 3 possible status for a transaction. Running, before commit and abort. Committing, before commit and end. Aborting, before abort and end. What about last Allison? Well, the latest log sequence number produced by that corresponding transaction. That's it. Okay? So that's transaction table. What about dirty page table? Dirty page table has 1 entry per dirty page currently in buffer pool. Okay? And it contains, obviously you need page ID, 1 entry per dirty page. Not every page in buffer pool, only those dirty page in the buffer pool. And you need, now this is what Victor was suggesting. You need something called REC Allison, record Allison. And this is to be different from page Allison. Page Allison is within the page. But this is in the dirty page table. And what is REC Allison? Page Allison is the last log record causing the page to be the last update operation to that page, right? That's what page Allison does. REC Allison is exactly the opposite. It's the very first log record. Okay? Cause the page to be dirty. But not the very first record go all the way back to history. Whenever this page is written to disk, it's no longer considered dirty, REC Allison will be reset. Yes or no? Follow me? So REC Allison is the first log record for the current dirty status. But observation you have to pay attention to though is that since this REC Allison this operation, there could be other update operation causing this page to be quote unquote dirtier, right? More updates to the same page. But I don't care about those. I only remember the very first one causing this page to be dirty. There could be additional ones make this page dirty, continue to be dirty. But I remember the first one. And that hasn't been written to this yet. Do you follow me? So that's my TT and DPT. Okay? You may wonder why you need these tables. Why you need these tables? Why you need these tables? Well, You need these tables for redo and undo purposes. You need this table for redo and undo purposes, which will become clear in a minute. And you need these tables for one thing I skipped really quickly just now. Checkpoint. And what happens during checkpoint? You may have heard checkpoint many times in a database system. Many people understand checkpoint as a snapshot isolation of the database, meaning that I stop the database from running at that particular point. I make sure all the changes are reflected to disk, then I move on. Right? Many people understand checkpoint like that. You know what? That's a completely wrong understanding of what checkpoint is. And what really is a checkpoint in a database system? Checkpoint does one thing and only one thing, which is dump TT and DPT to disk. That's it. That's all checkpoint does. TT and DPT are two tables kept in main memory, right? In a checkpointing process, what you do is you make a copy of TT and DPT and dump to disk, and dump the copy to disk. One subtle thing you need to remember is at the point you start checkpointing process, you make a copy of these two tables, and you start writing the content of these two tables to disk. While you're doing that, updates may continue to happen to these two tables. But you don't care. So what checkpoint does is to give you an image of these two tables at the begin checkpoint timestamp, not at the end checkpoint timestamp. So one thing I skip really quick is in a real database system, you will see start checkpoint and end checkpoint. There will be a gap between the two because it takes time to dump these two tables to disk. In this class, however, we make a simplification. In most cases, we assume this is atomic operation. Start checkpoint and checkpoint happen almost instantaneously. But in reality, what happens is at the start checkpoint, you make a copy of these two tables and write the copies of the two tables to disk. And during that process, updates may continue to happen to TT and DPT until you finish the checkpoint process. The point is, later on when system crash, you can recover the content of these two tables to the state at the start checkpoint, not at the end checkpoint. This kind of makes sense. Suppose you are in the middle of the line of checkpointing an airport into the airport, and terrorist attack happens. Those people pass the checkpoint completely will be okay. These people haven't started the checkpoint process will be okay as well, but what happens in the middle, you don't know. Who knows whether you are through or not, if you happen to be in that middle session. You know what I'm saying? It's kind of the same idea. Okay. Now we have everything we need, okay? Big picture, where they are. So we have log, which is on disk. We have the database, where each page has a page Allison, including those pages in the buffer. The page Allison for the same page may be the same or may be different for the image of page on disk and on buffer. And we have a master record. The master record is to tell you where is the last checkpoint, the log sequence number of the last checkpoint, so that you can quickly recover the last checkpoint when needed. You can go back to the log, oh, this log sequence number corresponds to the last checkpoint. Otherwise, you have to do a sequential scan backward to figure out where the last checkpoint is. So you use the master log record, master record. Whenever you do a checkpoint, you write to this master record on disk to tell you the log sequence number of the latest checkpoint. And then you have transaction table, dirty page table, and flush Allison. These are all in memory. Of course, buffer in memory as well. So these are the big picture, okay? Normal execution of transaction, you do series of reads and writes. For reads, you do nothing. For writes, you produce a update log record. And for commit, you produce a commit log record. For abort, you produce a abort log record. When commit or abort finishes, you write an end log record. Whenever you see a new update log record, you update the transaction table. You need to update running to committing or for every update operation, you do not necessarily produce an entry in DBT. When do you create an entry in DBT? Well, when a page is first become dirty, you will produce an entry in DBT. And when do you delete an entry from DBT? Well, whenever the buffer manager writes a dirty page to disk, you eliminate that entry from DBT. So buffer manager will interact with DBT, not anything else. Do you guys follow me? And we use straight to face logging and we use red hat logging. Red hat logging basically means what? Okay? That's red hat logging. Page Allison mask less equal than flash Allison when you try to write that page, of course. And when transaction trying to commit, last Allison of the transaction from the TT table must be less than or equal to flash Allison. Right? Yes or no? See some puzzle pieces. You guys need to pay attention, right? This is something you need to understand, and you have to understand. You have no choice but to understand. Okay? You have to understand. Because I will not graduate a student from my class who cannot do transaction and claim you have taken database class from Feifei and did well in it. Okay? And if you go to work for Google, Microsoft, Amazon, and you don't even understand transaction is, and you tell them, oh, I took this class from Feifei, and that's, I don't care about what they think about you, I care about what they think about me, right? So honestly, that's what matters here, right? So you need to understand.
When we are writing this transition table in DBT,
Louder?
this TTA we are writing to the disk.
We're writing to disk.
When we are writing it to the disk, and if that disk fails, is it in?
So as I said, that's an excellent point, but this is kind of covered by my earlier discussion, which is for this class, we'll assume that checkpoint is an atomic process. In practice, it may not be. That means during the write of TT and the DBD, system may crash at that right moment. In general, this is not a problem because you can always go back to the preceding checkpoint. Just ignore the current checkpoint. But for efficiency purposes, people try to do a little bit better than that.
And which disk is resides in?
Which one?
We are talking about two disks. One has the data.
Well, typically this resides in the same disk with you log. With the log file.
But there may be the cases that the log disk may also fail.
Well, typically you duplex the log, the disk holding the log and TT and DBT. You duplex. You use RAID 5 or whatever. Every bit should be written to two disks at the same time. I mean, log is small, so doing this doesn't introduce too much overhead. And the chance for two disks to fail at the same time, that's almost never happens. And your database disk fails too, right? Because even if both disks for log have failed, you still have a database disk. And if that gone bad, you should go buy a loss reactor. Seriously. At the same time, of course, right? Okay. Now let's look at what happened transaction commit. Well, pretty much what I said just now. Right? Let's leave this. Right? You commit. You make sure last Allison is less than or equal to flash Allison. You wait until that happens. If that condition is not met yet, you while loop. You wait until that happens, meaning that log record being flashed. Commit. And when commit returns, you write and to the log, and you eliminate the corresponding log entry for that transaction from TT. Simple abort. Simple abort means it's not a forced abort by system. Rather, it's transaction wants to abort itself for whatever reason. You get the last Allison from the transaction table, from TT table, and you write an abort log record before you start rolling back the actions. And then you simply do what? You simply do undo operations. How do you do undo? Well, you start from the last Allison, retrieve the log record. That must be an update log record. take the old data, override the new data. That's undo. And when you do that, remember, you need to document undo. Why? Why you need to document undo? Because you need to ensure automaticity means that you need to redo the undo if necessary. And you need to redo the undo if necessary. You need to redo the undo if necessary. If system crashes so many times, that must be a really bad system. I mean, you still haven't recovered yet. But in the worst case, you need to redo the undo. So that's why you need to document the undo by a CRR log record. So for every undo operation, you produce a CRR, compensation log record. Which means later on, when you see a CRR, you need to redo CRR, but do you undo CRR? You don't. Because undo CRR means undo the undo. That's bad. Undo means you didn't do anything. Right? Is that clear? And this is where the previous Allison becomes useful, because the way you undo this is you start from last Allison, you undo this, produce a CRR. Then what? Then you look at the previous Allison of the current log record and go to that log record and undo that, produce another CRR. And this becomes forming a chain that you can go back quickly for only the affected transaction, which is the transaction that's aborting. Otherwise, you have to linear scan the log, which can be expensive. Yes?
Do you need to make sure the CLR is supposed to this before you do the
Excellent question. Charlie's point is, while I'm doing this undo, and before I have finished running the CLR, system crash again. But remember, CLR is nothing else but another update operation, and we still obey the Red Hat logging requirement. Means that if the CLR is not written to disk yet, then the corresponding undo operation has no effect to database.
Oh, I see.
Because I'm still using Red Hat logging.
Yeah.
Update to the page can only happen when the corresponding log record has been documented. Did I answer your question?
Yeah.
That's a very good question, but I hope people understand what I'm saying, my reply to him. You still use Red Hat logging during undo. Undo is another update operation, and the update to that page cannot happen unless the log record has been written to disk, which is the CLR. If CLR has not been written to disk, that merely means one thing: that update has never happened yet. So you don't even have to worry about it. Very good question, but I hope I answered that question. Okay? It's a subtle issue, but it's a very important issue. Okay, so you just keep doing it, right? CLR never undo. That's essentially what I said. And CLR has one extra field. So the idea is you continue logging while undo. So CLR is nothing else but just like another update log record, except that it is documented for an undo update operation rather than a regular update operation. Okay? And CLR has one additional field, which is undo next LSN, which is nothing else but the previous LSN of the current log record you're trying to undo. Okay? So CLR contains redo information, but you never undo CLR. What do you mean you contain redo information? Well, you know the page ID, you know the offset, you know the old data. You don't even care about the new data anymore. Because to redo the undo, all you need to know is offset length and old data. You don't care about the new data. Yes or no? Do people follow me? Okay. At the end of all undos, I write a and log record. And I eliminate that corresponding entry from PT table. Checkpointing. So I talked about this already, so I'm gonna skip this. Okay? Checkpoint, basically you have begin checkpoint and end checkpoint. At the begin checkpoint, you make a copy of these two pages, two tables, and start writing them to this. When you finish writing that, you write end checkpoint. But for the purpose of this class, you can imagine this is atomic operation. Like begin and end checkpoint happen instantaneously. Okay, we're there. Okay, I need to present this, then I'm done. Then next lecture, I will then just use the next lecture to do a quick revision. and to do the quiz number 5, sorry. By the way, I released the last homework today, and it's unfortunately this has to be. I have to give you a short turnaround for this because I do want to do the quiz on Thursday. This homework by Thursday, and I will release the solution on Thursday, and you check it. Then we do the quiz on Thursday, and then I will do the review of it, and then all the stuff we talked about, effort to understand all the other systems. It's actually very easy to understand the other systems, the denial of the other systems.
If we have some record which is of variable length, and if we talk about that the next record has been updated, which is not yet committed to the disk, and the previous record has been committed to the disk with the change value of the variable, so the offset may shift.
No, I don't follow why there are 2 records involved. Each update touch only 1 record.
Yeah, update touch only 1 record. I'm talking about the 2 transaction in case of the variable size length records. If the offset of the record which is not yet committed to the disk has been changed, then
Well, but the point is they are all updating the same page from the buffer.
yes.
That's no problem. The buffer keeps doing the beauty of this design is the buffer keeps doing what it's been doing with no problem.
So we will update the offset value in the log file. My question is only that because the page.
Well, offset value is just for remembering what you have done. Can we take this offline because I really want to finish this and then I come back to this. All right. Crash recovery is the big picture. So last checkpoint, and system crash here. I will first do an analysis phase, figure out what I need to redo, then figure out what I need to undo. That's the big picture. Okay. Now let's look at what analysis does. The whole point of analysis is to figure out the smallest record Allison in 30-page table after the analysis phase. So after analysis, I need to figure out that value. Why you need to figure out that value? Because that's the earliest point from which you need to worry about what? Redo. The smallest record Allison, from this table is precisely the earliest point in time you need to worry about redo. Beyond that, you don't care about that. Because all those have been reflected this. But there's a subtle thing, which is what I'm going to say next is really important, right? The smallest REC Allison you figure out from the recovered 30-page table. The recovered 30-page table is not going to be the same as the 30-page table at the time of crash. Do you guys realize this? Why? Because the recovered 30-page table gives you the content of this page at what point? At this point. Things happen here are gone forever, unfortunately. The buffer manager from here to here may have come to the 30-page table multiple times and eliminate a bunch of entries. You follow me? So the real smallest REC Allison at the time of crash must be what? This is critical. Must be smaller than or equal to the smallest REC Allison from this point. Can only be smaller or bigger than. Depending on what it means, smaller or bigger, right? Must be the smallest REC Allison at this point must be after the smallest REC Allison at this point. That's the critical point. This ensures we are not missing any redo that's necessary. What about undo? Undo is easy. Well, if you recover the TT table at this point, for all those that are still active, meaning not committed yet, you just follow the chain to undo. That's it. And write CRR if necessary. That's it. Okay? Of course, there are some minor details we need to take care of. So analysis phase. The point is, analysis phase is re-establish the TT and DPT to this point, not to this point. Ideally, it would be super nice if we can recover them here, but well, unless you use what? Force and no skill. Then you exactly can do this, but we're not doing that. So you scan the log record forward from checkpoint. However, one thing that I forgot to mention is, by loading these two tables, you recover the state of TT and DPT at this point, right? However, we can do slightly better than that because our flash Allison might be larger than this. The flash Allison might not be up to date at this point, but it must be better than this. In the worst case, it's equal to this. But it should be better than this, somewhere in between, the flash Allison. Remember, these guys are lost, whatever. This is this, but that's gone. But at least I have flash Allison. My checkpoint might be here. So the idea is I can use these guys to what? To forward the state of TT and DPT as much as I can, so that I can be more efficient in redo and undo. Okay, that's what analysis phase is doing. Of course, this is tricky because having only the log record is not enough. Why? Because we never log. One thing we didn't log is what the buffer manager has done. We never log, or buffer manager has come to DPT and tell you to eliminate this. We never log that. Do you see what I'm saying? So this recover is an attempt to try to recover, but it will not be able to recover fully because we don't have that information anymore. However, as you can see, this is a safe recover because in the worst case, I have ignored all the action by buffer manager, and that only means that I have a smaller REC Allison than necessary, but that's okay. But that merely means I do a little bit more redo than necessary, but I'm safe.
Where do we use TT?
We use TT for undo, because you need TT to figure out what are the transactions that are still active at the time of the crash. So how exactly you recover TT and DPT using log record? This is what you do. You scan log record, you scan log forward from checkpoint. If you see an end record, you remove transaction from TT. Note that this is the recover TT from checkpoint, and you scan forward. All other records add transaction to the transaction table if it's not already there. If it is there, update the last Allison to whatever log record you have seen. Change transaction status to commit or abort when you see commit and abort log record. And for update record, if page key is not in dirty page table, add to DPT and set REC Allison to Allison. This is at least what we can do because I don't know when buffer manager will come and eliminate a dirty page, but I do know when buffer manager will come and create a dirty page entry because if it is not in my dirty page table and I see a log record updating this page for the first time since checkpoint, buffer manager must have come to dirty page table and created an entry for it. Must have done that. So I will just duplicate that action. Right? Because this must be a dirty page. Okay? At annual analysis, we get a really good understanding of these two tables at the time of crash. Not exact as they were at the time of crash, but very good understanding of that. For two reasons. One is I don't know the buffer manager action, and I lost this guy forever after flash action. But pretty good, fairly close. What about redo? Well, go to the smallest REC Allison and scan the log forward. That's it. And for each update log record or CLR, you need to redo CLR. Remember? That's what I said earlier. Because that represents an undo operation that might have not been permanently reflected on this yet. Seeing a CLR merely means what? Merely means somebody else was trying to do an update for that undo operation. Whether that undo has succeeded to this or not, I don't know. So potentially you need to redo that. Right? So for every update of CLR, you need to redo the action The naive solution is simply redo the action. Then you are guaranteed to be right. But we can be a little bit more efficient in what we do. So one of the three conditions, if you see one of the three conditions is true, then you don't need to redo the corresponding undo or CRR log record. Why? What are the three conditions? One is affected page is not in the dirty page table. If that's the case, you don't have to redo this. Because that means at some point the buffer manager has come and removed this from the dirty page table. So the changes made by this update log record must have been reflected by the disk. You follow me? Second, affected page is in dirty page table, but REC Allison is greater than the current log sequence number you're trying to redo. What does that mean? That means this log record has caused this page to be dirty, but then at some later point, the buffer manager has come to the dirty page table and tell you this dirty page is written to disk. And then after that, somebody else, which is REC Allison, which is after this log, has made the page dirty once more. That's why you still see this page in the dirty page table, but not because of this, but because of this guy. That's why you don't have to redo this. Do you follow me? You don't have to redo this. Note that these are referring to the same page, right? Page I. This has caused this page to be dirty, so it was in BPT at some point. However, buffer manager came and deleted because it was written to this. Then this guy made this dirty again, so it's inserted back with this. And of course, there may be more records making the same change, making more changes to I, but this is the first one that's still causing the page to be dirty at the time of crash. But this was not. This has been taken care of. That's why you don't need to redo this. If none of this is true, meaning that it's in the page table and REC Allison is after the Allison, this Allison is like that. So this is my Allison. Then you do need to worry about redo this, unless what? Unless page Allison of this page not captured by our recovery process, because we didn't log what buffer manager is doing. The last change reflected this is already ahead of this change caused by this Allison. Well, if none of this condition is true, you redo and you set page Allison to the current Allison. That's easy, right? That's the last change made to the page. No additional logging, no forcing. The point is you don't log redo. You don't log redo. Why? Because the original log record is good enough for redo multiple times already. You don't log redo. It's not necessary to log redo. The example, I obviously don't have example to go over that, so you will go over that yourself. I have to overrun another 2 minutes to do the undo. Undo is easier than redo. What undo does is from the analysis phase, you have recovered the TT table. From the TT table, you grab all the active transaction after the analysis phase, and you look at their last LSN. These guys. Note that you have two choices, which is undo transaction one by one. Now, obviously doable, but if you think about it, what happened is you're doing this. Then come back, then come back. So a more efficient approach is to undo all transactions in one backward scan of the log, rather than undo transaction one by one. And that is essentially what happened here. I maintain a priority queue of last LSN, and I sort them based on the log sequence number. The largest one is at the head of the queue, and I always pop the largest one from the head of the queue. So I undo like that. So how do I undo? Well, very simple. Pretty much like the typical, the normal abort operation. When you undo an update log record, you write a CRR. When you see a CRR, you don't undo it, you do nothing, but you look at the undo next Allison and add it back to this queue. If you undo an update log record, you undo it, you write a CLR, and what? You add previous Allison of the current log record you're trying to undo to the queue. Now that will be the next log record to be undo for the current transaction. But you don't undo it immediately because you undo by the sorting order of this log sequence number of all these transactions. That's it. You continue doing this until this to undo list becomes empty. What happens if system crash in the middle of this? That's okay because you keep logging while undo through this CLR. And CLR will be redo by the redo operation. You never undo.
Do you block new transactions while you're recovering?
Yes, during recovery process, analysis, redo, and undo, no active transactions are allowed to move forward. With that, I stop right here. That's been released, which is due on Thursday, which is not too bad, I guarantee you. And then we will meet on Thursday. You can go over yourself. I'm more than welcome to answer emails or questions you may have. Then on Thursday, we will do the quiz, release the solution, do the quiz, and revision and review, discuss NoSQL and all that stuff, whatever interests you. We will do that on Thursday. Final exam is on the 18th. Okay, all right, thank you.
That was